So if links contract then, does it mean they contract in all directions? The answer is no. The contraction only takes place in the direction of motion. Okay, and so if for a moment we look up at the data projector, we can see what would happen if a triangle moved to the right. We see that the vertical side of the triangle would remain unchanged, but the horizontal side would be shrunk from some original length x to some final shorter length L. And that's the part of the motion that would satisfy the relativistic formula that I showed you. All right, so with these ideas in mind, let's try to combine this together. Let's say that we've got a particle in a laboratory frame that moves at 0.8 c. across the lab. And this is a 100-meter long lab. So I could call this distance then L naught. And that L naught value is going to be 100 meters. Let's say the velocity here is 0.8 c. And so let's find first A, the distance that the particle travels relative to the lab. Okay, so is this a hard question? Well, no. This is trivially easy because relative to the lab and the observers in the lab isn't moving. And so therefore it's just 100 meters. So that's the easy one. You get that one for free. B, let's find the time that it takes for the particle to move across the lab, relative to the lab. Okay, well, the time for the particle to move across the lab relative to the lab is just going to be the distance divided by the velocity. And so neither one of those are contracted at all. Okay, and so we could just say that L naught, distance, is equal to rate v times time. Okay, so in this case, we're just looking at the original rest time of the lab, and so it's just rate times time equals distance. Okay, so the time relative to the lab is just equal to 100 meters divided by 0.8. Now this time I'm going to have to actually multiply it out. I don't get to cancel the c for this example. So we don't want to always get used to doing that and then not be able to actually work out a number. So this is 3 times 10 to the 8 meters per second. Okay, and so that gives me 4.16 times 10 to the minus 7 seconds. Okay, not much time, but certainly measurable. Okay, so that's the time that it takes for the particle to move across the lab relative to the lab. Now, let's get a little more challenging here. Let's find the distance that the particle moves relative to the particle. Now, technically here, the answer to this question is 0, because the particle isn't moving in its own frame of reference. So what I really mean here when I say this is what distance does the lab move through the particle, going from one end of the lab to the other? That'd be a little more correct here. But I didn't want to state it that way to begin with. From end to end, how much distance does the lab move through the particle? Einstein is quoted in one of his trips around Switzerland to asking the conductor, at what time does Zurich arrive at our train? And so that's what happens when you get your head scrambled with this relativity stuff. You start getting very weird. But that's actually a little more correct, is to say how much distance does the lab move through the particle? Because the particle, from its own point of view relative to itself, isn't moving. It's in its own inertial reference frame, and it's the lab that's moving through the particle. And so here's the particle then, and here's our lab. And because the lab is moving through the particle, this distance is going to be contracted. So it would be L naught times the square root 1 minus v squared over c squared. Okay, it's going to take less time from its own point of view, and it's going to move less distance in that smaller amount of time. But it'll still be the same relative velocity. And so you've got this much longer lab being length contracted. And that's what the particle sees then, is the lab moving through the particle and only having that length. Okay, so we can then write this then as L equals 100 times the square root of 1 minus 0.8 c squared over c squared, which is 100 times the square root of 1 minus, we've done this one before, 0.64, or 100 times square root of 0.36, which is just 100 times 0.6, or 60 meters. That's how much distance is traversed by the lab as it moves through the particle. Okay, because the particle is traveling through an object that's moving through it and is length contracted, just like the meter stick is length contracted. Here, the lab is length contracted. And so, if I were moving, let's say at 80% the speed of light, through a room full of students, you would think, well, you look pretty funny because your head's really oval, much skinnier than normal, and I would be getting a bigger laugh because I would see the entire classroom filled with oval heads, moving away from me in the opposite direction. So we'd each see each other as being shorter than the other one. And we'd also see each other as moving more slowly. Okay? And so it's not the kind of thing where you have an absolute reality. You go, well, if I'm going slower than you, how can you be going slower than me? Or if I'm shorter than you, then how can you be shorter than me? But that's the way it is in relativity. You're both right from your own points of view. Okay, so that's C then, the particle. And by the way, for a lot of these problems, I'll be giving you exercises to do that will have a due date that encourages you to watch these videos in a timely manner. Okay, and so you'll have one to do that you'll get some points for. That'll be very similar to this one, so you can just use this one as reference to solve it. And then finally, in D, let's find the time that the particle moves across the lab relative to the particle. Okay, so it's still relative to itself. How much time is elapsing on the particle's clock as the lab moves across the particle? And so the answer there is that you have rate, which is the velocity, times the time. Now this is going to be an expanded time. So the rate times the time, in this case, equals I'm sorry, there's going to be a contracted time. Whoops. This is velocity times contracted time equals contracted length. Okay, so relative to the lab, you've got a velocity through a larger time equals a larger distance. But here, there's less time. So this is what we call T naught. Okay? And that amount of time is going to be equal to x over v. So we can write T naught equals x, which is our contracted length, right? And so that's going to be, what did we get for that? 60 meters divided by v, which is 0.8 times 3 times 10 to the 8 meters per second. Okay, so we're expecting this time is going to be less than the time that's measured in the lab. This is the lab time that we calculated in part B. This is the particle time that we're calculating in part D. So you can see the math here is not bad, but the concepts can be a little daunting. Okay, you have to keep track of which thing is moving relative to which other thing and which equation to use at the right time. But the actual math itself, not all that bad. And so, and that's typical for these problems. They tend to be very abstract, but maybe not as heavy of math as what you've seen before. Okay, so that gives me 2.5 times 10 to the minus 7. Let me just punch that out one more time, make sure that's right. There we go, that's better. 2.5 times 10 to the minus 7. Seconds. Okay, so if we compare T naught, that's the time that elapses on the particle's clock, to T, which is the time that elapses on the lab's clock, we see that T on the lab's clock is larger, just as we saw before. And by what factor is it? Well, if we take t naught and multiply it by 0.6, right? What we're going to get is this time will turn into this time. Okay, so this is consistent then with t equaling t naught divided by the square root of 1 minus v squared over c squared. And it had better be, okay? Because in other words, t here is 4.16 times 10 to the minus 7. This is 2.5 times 10 to the minus 7. But then that's divided by the square root factor, which is here, 0.6. Okay, and so 2.5 divided by 0.6 is 4.16. So by working this whole thing out, we were able to also verify the time dilation relationship between the rest time and the true time for this example. And so going back here to this expression then, remember that this then is the time that the clock would measure, or that would be measured by the particle on its own clock. And so this is sometimes called our proper time. And this is the expanded time, so that the particle actually seems to last longer, take a longer journey while doing the same thing, which is moving from one side to the other. Now, one thing that this kind of brings into focus is what happens if you flip reference frames and you go, let's say, from the particle and the Earth so that they're watching each other in the opposite direction. So in other words, like in that problem that we looked at earlier, where we had the rocket moving by the stationary Earth, what if we said the rocket was stationary and the Earth was moving away from the rocket? Then how could we resolve that? So what we would see here then is if, let's say, we were inside a laboratory and we fired a beam of light that went up and back across the lab, and the lab was moving away from the rocket like this, then what the rocket would see would be the beam moving along this path, the lab would see it moving along that path, and so you would have an exactly symmetrical opposite viewpoint of the rocket viewing the Earth, so that the rocket would see this distance as being shortened and would see the time would slow down here. So the Earth sees the rocket's time is going slower, but from the rocket's point of view, you could set up an exactly symmetric situation and would see the exact opposite effect, where the rocket would see the Earth's time as going slower, and more time would elapse on the rocket's clock relative to the rocket. Okay, and so that's relativity carried to its ultimate extreme, because each one sees the other one as moving more slowly than normal.